Welcome to this AP guided practice on photoelectron spectroscopy. The first thing I want to do is address Coulomb's law. And so in Coulomb's law, we don't actually need to, for AP chemistry, calculate values, but you might be able to use this as justification by using arbitrary numbers, which I'll show you today, or just in your justification, we want to understand what's going on with Coulomb's law. So the first thing that we have is we have a force. And so this force on this side can be either for attraction. Okay, so we could have attraction. And that's going to be if you have a positive and a negative charge. And then, of course, we could have actually repulsion as well. And so if you had two positive charges or you had two negative charges, which is usually where we get into some information, because two negative charges could be something that we call electron repulsion. So keep that in mind as we kind of work through some problems. And then as far as the Q values, so Q is going to be the magnitude of our charge. Okay, so magnitude of charge, a little bit smaller there. And think about that can be either your protons or your electrons. Okay. Electrons generally will just have a charge value of 1. So for our electrons is just a -1. But when we're dealing with our protons, we actually want to think about something that we call the nuclear charge. We kind of distinguish these here, all under this Q value. Oops. Okay, and so for nuclear charge, this is going to be the sum of our protons. Okay, so sum of our protons. Okay, so the total value. The other thing that we have is we have our R value. Okay, so R is the distance of particles. And so with these, we know that as the distance electrons are away from the nucleus, then that's actually going to increase our distance. So the further those electrons are away. So as we increase our energy level, our principal energy level, principal quantum number, or you could think of this as electron shells, we are increasing the distance between the nucleus and electrons. Okay. So we're going to take a look at some photoelectron spectroscopy graphs, PES graphs. And a lot of times these graphs are going to have something called binding energy as the x-axis. Okay, so we're going to see this binding energy. One thing to kind of keep in mind with the binding energy is a lot of times this is energy required to remove a particle from a system, and for us specifically, it's the energy to remove an electron. Okay, that's really, really similar to ionization energy. I think technically in how we get that data might be a little bit different, but for our purposes, we are going to consider these to be interchangeable terms, and both of them are a measure of energy to remove an electron from an atom or ion. Okay. So what does that look like for different electrons as far as Coulomb's law goes? So why does it take less energy to remove outer electrons versus our core electrons or our inner electrons? So core electrons are going to be the inner electrons. So core electrons, okay, versus valence or the outer electrons. So the big deal here is that these core electrons are going to be closer to the nucleus. So this is a distance issue. Closer to nucleus. So that distance is less. That's that R value. Resulting in greater force. Okay. The opposite is the case for valence electrons, and so for our valence electrons, we know that they are further away. Okay, so farther from the nucleus, which means distance, that R value again is greater, resulting in less force. And I guess in this specific case, this is going to be attractive force between those valence electrons and the nucleus. So let's go ahead and take a look at a PES graph here. This first one we have is for nitrogen. This one's for nitrogen. And what we can do is we need to understand a couple of things. Remember, we can talk about the axes as being binding energy or ionization energy. So binding or ionization energy. You'll see both sometimes depending upon where the graphs are coming from. And one thing I really want you to notice is that in this particular case, the highest value is closest to the y-axis. And so this is going to be closest to the nucleus. And this one over here is going to be farthest. Farthest. So just kind of watch that. You also have to watch on the other side, this is going to be number of electrons. I see these graphs, and you'll see some even in my examples, where they aren't always one line as one electron. Okay, so we know whenever we are looking at these, the electrons that are going to be closest to the nucleus are going to start with that lowest energy level, and that is going to be energy level 1. And so we know that we have this is the 1s, okay, and there's 2 electrons in there, so 1s2, and so we know that the principal energy level is 1, okay, so N is the principal energy level. Actually, I'm not going to do it that way. So N equals 1. And then from there, it would go up to the 2s, and we see 2 electrons in there, and then it would go to the 2p, and so each one of these peaks is representing some of those. Now 2p, there's 3 electrons in there. Okay, and so for nitrogen, we know that we can write this as 1s2, 2s2, and 2p3. And this actually is really nice because this is the data that confirms all these electron configurations that we write. So let's take a look at another example. And in this case, we have oxygen. And so oxygen, again, same type of graph. We are going to see that we have, for oxygen, 1s, 2, 2s2, 2p4. Now, really importantly, remember that your valence electrons, okay, These are our valence electrons. And they're going to be the highest energy level, so that's the n equals 2. So highest energy, G level, okay? So we're dealing with energy in a couple different ways. They're the lowest binding energy, but they're the highest energy level, and that's the 2, okay? The 2 here tells us that they're the higher energy level. S and P orbital electrons, okay? All right, and then we can just go ahead and write this out. So we have 1s2, 2s2, 2p4, and that matches up with what we have for oxygen. So from a graph like this, we would be able to determine what the electron configuration is, and then from that we can determine what the element would be. Okay, so now what happens when we start to get into comparing some of these? And this is a bit tricky in some cases, but I just kind of wanted to go there today and take a look at this. So in this graph, notice that we are comparing oxygen to nitrogen. And so I'm going to go ahead and on here, our oxygen, we have, we flip this around. So just notice on this one, we have in this graph that this is going to be closest to the nucleus, and over here is going to be farthest from nucleus. Okay, so our oxygen, of course, again, we're going to have our 1s2, 2s2, 2p4, and our nitrogen is going to be 1s2, 2s2, 2p3. And what we want to notice is how do the energies for each one of these kind of relate and what's going on overall. So I'm going to kind of scooch over to the side here. And when we are comparing nitrogen to oxygen, so nitrogen and oxygen are in the same principal energy level or principal energy number, okay? In the same period on the periodic table. So they have the same energy level. We said that was n equals 2. That's where the valence electrons land. Okay. So then we have to account for what's the difference here. Well, we know that nitrogen has 7 protons. Okay. And if we wanted to look at the orbital diagram, we know that we have for the valence electrons only, I guess I should do that. Okay, so for valence electrons only, we're going to have the 2s, we have 2 there, and then 2p, we have just 1 in each orbital. So I'm going to draw that ahead of time here. For oxygen, we have 8 protons. I'm going to draw our valence orbital diagram here as well. 2s, and then the 2 p's, so the s is full, and the p's look like this. So the first thing that we notice is that the core electrons, okay, or the s electrons, I guess I should even say, are held a little bit tighter by oxygen. And that's because we have more protons. And so we see that we have on oxygen, we have a greater charge, greater nuclear charge, resulting in greater force. attraction. Now, the sticky bit becomes what is going on with this P4. So we would expect that that would actually be held tighter because of oxygen's nuclear charge. But in fact, what happens with this is the first doubly occupied p orbital. And so we see something kind of strange that happens. So right here, this first doubly occupied p orbital, I'm going to talk about this specifically. The 2p4 has the first double occupied orbital, p orbital, I guess I should say. And what happens as a result of that, it's going to cause electron repulsion and slightly decrease binding energy. Comparatively. That might not happen with all of those. That's really going to be in that P4 position that we see that little bit of an exception. So this is an exception to our trends. When we start talking about trends, to trend. Okay, so most of the time that would actually not do that. We can actually even take the Coulomb's law equation. We can actually kind of arbitrarily plug some numbers in, and that's something I'm happy to do in class for you if you would like. Okay, let's do the same thing, but now looking at nitrogen versus phosphorus, which are in different energy levels. Okay, so nitrogen and phosphorus are in different periods. Okay, so different energy levels. And it's really all about trying to describe what is happening with the data that we see. Okay. If they're in different energy levels, electrons are at different distances. Okay, so let's go ahead and take a look. I'm going to zoom in on this and let's just analyze what we have for the graph here. So for nitrogen, let's do nitrogen first since we've been working with it. We have our 1s2, our 2s2, and our 2p3. For phosphorus, we have our 1s2, 2s2, 2p6, 3s2, and 3p3. Okay. So what we notice is that phosphorus is actually holding the core electrons with greater force of attraction compared to nitrogen, but the valence electrons have different energy values based on the fact that we're in the second energy level for nitrogen versus the third energy level for phosphorus. So let's describe that over here a little bit. Okay, so nitrogen is in the n=2 energy level. Okay, it also has 7 protons still. That didn't change. Whereas phosphorus, n=3. Okay, so we have 15 protons And what we're seeing is that there's a greater attractive force, so greater nuclear charge, holds those core electrons with greater force. But the challenge is when we're talking about the amount of energy to remove those valence electrons, those electrons that are really going to be involved in bonding, because we are in the third energy level, there is less energy that's going to hold those in because of the greater distance. So we have greater distance of valence electrons resulting in less force of attraction to hold those there. Okay, so it's really all about putting together what's happening with Coulomb's law with what we are seeing in the data. So just kind of think of it that way. One of the things that oftentimes is very confusing for students the first time we start going through electron configurations and orbital diagrams is, why are we seeing the 3Ds and the 4S's? What's going on with those? And so one of the things to keep in mind here is that the 3D actually has greater energy of attraction or ionization energy or binding energy. So the 3D has greater binding or ionization energy compared to the 4S, okay, which is right down here. And so one of the things that we know is that for a lot of those transition metals, okay, so those transition metals lose the 4s electrons before the 3d electrons. And so in how they fill, they'll fill in the 4s first and then the 3d, but a lot of times when we're losing them, they'll lose from the 4s first and then from the 3d. It's a little oversimplified. There's some other stuff that kind of goes on with them, but that's just something to keep in mind if you're asked about electron configurations for ions, that we're seeing the loss of electrons from the 4s before the 3d or from the 5s before the 4d. So just something